public lecture was going to be part of a study group we were going to host on clean and sustainable growth at the University of Nottingham, but obviously things intervened and meant that we couldn't go ahead and do that, although we may try to do a virtual study group in the future, depending on how the one that Dawn just mentioned is going. But we thought it'd be really nice to continue to deliver the public lecture that we had arranged with Vicky as part of that study group. And I guess it's quite important for us to try to carry on doing some of these things and keep communicating about the science that we're doing and so on. So very pleased that Vicky can give the lecture today. Vicky Pope started out as a mathematician at the University of Cambridge and went straight from there to the Met Office to undertake her PhD and only left last year. And she had a long and varied career there working on climate change modeling, but also lots of exposure to other types of work, including business development and management and so on, and now is involved in all kinds of external activities, including a maths education charity. So, if you have questions for Vicky more broadly about career development and that sort of thing, then there's an interesting point of contact there. So on that note, I'll hand over to Vicky, and she's going to talk to us about climate change, how mathematics can help us to respond, and I'll talk to you again a bit later when we come back for questions. So thanks very much, Vicky. Over to you.
Thank you, Marcus. As I think this is probably new to many of us, this is the first time that I've done a lecture in this way, so hopefully it will work. Hopefully the bandwidth will hold up. What I hope to demonstrate today is the importance of mathematics in both understanding climate change and in communicating it as well. And I want to start off by talking about some of the data that is used to demonstrate that the climate is already changing. And not working. And an important aspect of this is that in order to communicate about climate change, one of the things that we do a lot is show graphs. And here's a graph of the carbon dioxide changes at the Mauna Loa Observatory in Hawaii. And you can see this inexorable rise in carbon dioxide from the 1950s. Now, I find if I look at a very compelling graph, that tells me an awful lot about what's happening. Just to give an illustration, the current crisis, I first realized how significant the impact of coronavirus would be in the UK when I read an article by somebody called Thomas Peo on Medium, which basically distilled some of the science and gave a very distinctive graph, which everybody is now familiar with. As soon as I saw that graph, I thought, this is really serious. Why hasn't the government done anything already? And it really brought it home to me, but it also brought it home to me the fact that other people didn't react that way, that the way that I view information on a graph is quite different to the way many other people do if they don't have a background in mathematics. I'm guessing that many of the people in this audience have some link to mathematics because of the nature of the way that this lecture was put together. And probably when you see a graph, you do find it very compelling. But it's worth remembering that one of the things that we need to do is to make sure that everybody has some basic understanding of mathematics to help them to interpret some of the really complex issues that are important in the world today. And of course, what we don't want people to do is, there's a very significant issue going on at the moment, but climate change is also important. And it has a very significant effect over a much longer time scale. But for many people, until they actually see things in front of them, on their own doorstep, it's very hard for people to react. And I think the way that people have reacted to this virus is very illustrative of that. And that's one of the things that we need to understand in terms of how we respond to climate change, because the threat is obviously on a much longer time scale. And we're only starting to see some of the effects now, but the biggest effects will happen later and when we'll already have stored up some of the problems. So just showing you some of the graphs that show how climate is already changing. So that's the carbon dioxide measurements. It's worth bearing in mind that these measurements were, they weren't always that well protected. They were done by Keating and his co-workers. They had to fight to get funding to keep the observations going. And obviously without those, we wouldn't have the long time scale record that we have. But they weren't viewed as important because they weren't new. It was, measuring more of the same thing. Doing measurements is always can always be very difficult. So it's worth bearing in mind that sometimes the boring, mundane things are the things that turn out to be the most important. So carbon dioxide has increased by around 35% since 1958. Global temperatures increased by more than 1 degree since 1850. Now, obviously, we don't have the CO2 measurements, direct measurements going back beyond the 1950s, but there are other ways that we can look at the CO2. So we know that that's been increasing as well. Now, just seeing the graphs doesn't tell you that they are linked to each other. We have to use something else to actually establish that link, and that's where climate models come in, and I'll come back to how those work a bit later. The oceans are becoming more acidic because of this carbon dioxide being absorbed into the ocean. So that's having two effects. One thing is that it's slowing down the global warming because some of the carbon dioxide is being absorbed both into the ocean and into the biosphere generally on land. But that extra CO2 in the ocean is threatening marine ecosystems. So looking at it in terms of extreme weather, so looking at the global mean temperature, an increase of 1 degree, well, it doesn't really mean very much to people because you see variations of much more than 1 degree every day. So we need to translate, we need to understand what impact that has on the weather. And it's the daily weather and the extremes of weather where the impacts are obviously seen most clearly. So this diagram just illustrates the changes in weather and climate events compared with changes in events that have nothing to do with weather and climate. So if you look at the red bars at the bottom, which is geophysical events going from 1980 up to 2015, you can see that there's variations from one year to the next, but there's no systematic change. When you start to look at the meteorological events and the hydrological events, climatological events, particularly the hydrological events, you start to see a trend in those events. So these are things like flood, mass movement of water, extremes of temperature, drought and wildfire, and we're seeing a steady increase in those. And again, using models, we can actually make an assessment of how much we'd expect those to vary from decade to decade, and how much we're actually seeing that, and whether how much of that is due to global warming and how much is just natural variability. And the statement in the IPCC, the last IPCC report, was that more than 60% of extreme events studied to date were made more likely or more severe by man-made climate change. So that underlying that very broad statement is a lot of science that means that you can give some confidence to those numbers that are in that statement. So we're already seeing changes in extreme events. So the other way that mathematics is important is, of course, it's central to the way that we actually understand the climate. So we create mathematical models of the climate in order to be able to understand both how it has changed in the past and how it will change in the future. And these are the same sort of models that are used for weather forecasting. We have to add extra processes in for climate change because there are some things that are important on a climate timescale that aren't as important on a weather timescale. But essentially, they use the same models. And indeed, in the Met Office, they actually use the same model for both. And so there's an awful lot of people working on developing models to make these things work. And I'm going to now describe the science that we have to represent in those models. And this just gives a simple illustration of what drives the weather and climate. And these are all things that you would see in a climate model if you look at the Fortran code, complex as it is. So we've got the energy cycle, the water cycle, the general circulation, and then what we're doing to change that balance. So the weather and climate is in a balance because of all these cycles. But as we change the greenhouse gases in the atmosphere, that changes that balance. So if we look first at the energy cycle, essentially the whole system is driven by energy from the sun. So we've got incoming ultraviolet radiation, and some of that sun's energy is reflected by the clouds. Some of it reaches the Earth's surface, and some of it's absorbed by the atmosphere. We then have heat radiated from the Earth. So some of that, again, gets absorbed by clouds and re-emitted. Some of it passes straight through, and then you're also getting emission from the atmosphere. Now, in the atmosphere, there are lots of different gases, and there's also water vapor. So the greenhouse gases, with the carbon dioxide and methane and other greenhouse gases, act to trap the heat like a duvet. So essentially, some of that heat that's being radiated from the surface gets trapped by the CO2 and then re-emitted to space. And that trapping of the heat near the surface means that the average temperature of the surface of the Earth is 15 degrees centigrade instead of minus 18 degrees centigrade. So it's worth bearing in mind that if there weren't no greenhouse gases in the atmosphere, there would be no life on Earth. The greenhouse gas and life are interdependent with each other. And it's very important that we have greenhouse gases. It's just that as we're changing the amount of greenhouse gases by burning fossil fuels and other pollutants, we are changing that balance, and so we're increasing the temperature. So the other aspect of this is absolutely critical is the water cycle. So as you warm up the surface, the water evaporates from rivers, lakes and oceans, and it condenses to form clouds. You also have a loss of water from plants, soil, animals and people. Obviously, once the cloud form, if they form with enough water droplets, that can then fall back to land as precipitation, either rainfall, snowfall, and the water is carried down the hills into rivers. So rivers carry some of the water back into the sea, and so you've got this cycle of water going on. And the water obviously is vital for life, but it also plays a really important role in global warming as well, because water vapor is also a greenhouse gas, and so that is one of the things that is absorbing temperature and causing warming at the surface. As the temperature warms up, there's more water vapor getting into the atmosphere, and so we get what we call a positive feedback, which means that the warming is enhanced because the water vapor is increased. Of course, clouds also have an impact on global warming, and one of the biggest challenges in climate modelling is how we represent the clouds in the models, because some types of clouds actually cool the atmosphere and some types of clouds warm the atmosphere. So very high cloud, for example, which is often very thin cirrus that you see on a sunny day. There might be some outside. I've got my blinds shut so I can't see, but that very thin cirrus cloud tends to let the sunlight through. You know, still be very sunny, but it traps some of the infrared radiation coming from the ground, so it tends to warm the climate. The lower cloud, that tends to be thicker and darker, will tend to cut out some of the sunlight, and that tends to cool the climate. So actually understanding the detail of how that cloud forms is a really important part of the climate model, and it's one of the challenges. And when I was working on climate models 20 years ago, it was a big challenge. It's still a big challenge. It's much better represented now, but it's still a big challenge in terms of understanding that how much climate is going to change in the future. So moving on now to the general circulation. So this is to do with the kind of average way that the winds behave and redistribute heat around the globe. And it's not just the winds in the atmosphere, but also the ocean currents are really important in redistributing heat. A lot of the heat that we have in the atmosphere is, obviously heats up the ocean, and that heat also gets distributed through the ocean. So on balance, you're tending to heat up the equator more than the poles because that's where more sunlight is, and these winds and ocean currents tend to redistribute that, so moving some of the heat towards the poles. So one of the things that happens when you warm up the atmosphere through global warming is that pattern of winds changes, the weather patterns change. So we may, for example, get more storms in the UK. We may get some periods like we've had recently where we've got high pressure and very dry weather for a period of time. One of the things that we think might happen in the future is that the kind of stability of the weather in the UK will change, so that we get longer periods of high pressure, longer periods of storms, which paradoxically means you could get more droughts and more flooding, which is rather a shame if that happens, but we're seeing some evidence of that kind of thing happening. So through the thread of this, I've been talking about what happens when we increase greenhouse gases, and there are many ways that we can change the balance in the atmosphere. So by burning fossil fuels in power stations, in transport, by chopping down trees, changing vegetation, burning vegetation, all of these things increase the amount of greenhouse gases. One thing to bear in mind is that some of the other things that are produced in industrial processes and in burning in fires, for example, are aerosols. So these are things like the nitrous oxides, which cause air pollution, which cause a lot of problems in cities, of course. They actually tend to, on average, to cool the climate. They have a complex effect and they have an interaction with clouds. But because they cool the climate, then that you've got these different types of pollutants are having an offsetting effect. One of the things that obviously people have been trying to do in the last 20, 30 years is to decrease the amount of aerosols getting into the atmosphere, the amount of air pollution, because it has very detrimental effects. As we decrease that air pollution, that tends to mean that the warming is enhanced because it's not offsetting some of the greenhouse warming. So all of these things have to be represented in climate models, and we can translate all of these processes into equations. And this is what we do in a climate model. So this is an example of how we basically divide the world up into little boxes. And then within those boxes, we can solve the equations for the atmosphere, the chemistry, the biology, and so on. And we use these models then to test hypotheses about how the climate system might change. So what we're doing when we look at future climate, we're doing a what-if experiment. What if we manage to go back to pre-industrial levels and we have previous carbon dioxide amounts? What if we carry on increasing carbon dioxide at the same rate we are now? What if we manage to decrease it, but not so much? We can then understand how the climate might change in the future. Of course, there are unknowns that we can't represent in the model. There are some things which we know are not well represented in the model. And so we have to try and capture that uncertainty in our calculations to say that this isn't telling us what exactly is going to happen in the future, but it's giving us an idea of what might happen and what risks we're running in doing that. So this just summarizes really those processes that are important for climate change. And you can see there's all the atmosphere processes that I mentioned. The biology is important because plants absorb carbon dioxide. So if at the moment we're reducing the climate isn't as warming as fast as it might be because a lot of that carbon dioxide is being absorbed. But as I mentioned before, as the temperature increases, that the ability to absorb carbon dioxide decreases. I've included some photographs in this slide because it's worth bearing in mind that we divided the world up into little boxes. If you look at the previous slide, but they're actually quite big boxes. They can be sometimes 100 kilometers across. You look at these processes when you look at the photographs, they're very complex. They've got lots of very small scales. You can't represent all the detail in those clouds, for example, or in the ice. You have to average those properties. You have to make an approximation, and that's what we have to do. We do something called parameterization in a model in order to do that. And we test the parameterizations we use in a climate model against more detailed models so that we can make sure that we're doing things as well as we possibly can. So this slide here just illustrates the carbon cycle protection that I mentioned. So these are observations of carbon dioxide emissions. And you can see that the emissions go up quite steadily on the red curve there. And then on the black line, you've got quite a lot of variation in the actual atmospheric, the growth in the atmosphere of CO2. And what you find is that those peaks in CO2 growth correspond to warm years. So basically, you're already seeing an indication that in warm years, not as much CO2 is absorbed into the biosphere, as more of it ends up in the atmosphere. And that just illustrates what we might expect to happen more in the future. So what about the outputs from these models? So this is an illustration of a kind of climate change signal. So if you look on the right-hand side of this diagram, you can see going right the way through to 2300, how we might expect the temperature to change. This is global average temperature, and the red shaded area shows you the higher end scenario, which is the track that we're on at the moment, but we hope to avoid. And then the other ones show what happens if we're able to mitigate the climate. If you go back over to the left-hand side of the diagram, this is looking at what we call paleoclimate. So these are prehistoric climates using things like ice core data, tree ring data, going right back 60 million years. And if you look at, I don't know whether the cursor's working on here, if you go right back, you see that the sort of temperatures that we'd be getting in 2100, we haven't seen since around 5 million years ago. And if you go to 2200, you're looking 40 million years ago. So we're taking the climate into a territory that we haven't seen before, certainly in historic memory. We're going back to an Earth that was very, very different in terms of what the climate was like. So it just gives you an idea of the scale of the change that we're talking about. So looking at just now going to 2100 and what we can do if we to reduce emissions. So we're seeing here the red curves, which are the same as the red curves on the previous slide. This is a high emission scenario, what we've called RCP 8.5. It's a technical term, but basically it means pretty much business as usual, carrying on increasing greenhouse gases. If we look at the other curve, which is a 2.6, the low emission scenario, you can see that global average temperatures are increasing by around 1 degree, and that's relative to temperatures from 1986 to 2005. So that's overall, from pre-industrial times, that's around 2 degrees. So that just gives you an illustration of the kind of scale. If we make major changes in our emissions that we could achieve, but these are very major changes. So this is another way of looking at that. So to stay within 2 degrees, which is the lower curve that I showed you, you can look at how much carbon budget we've already used and how much we have left, and use this hourglass as an illustration of that. So so if we look from 2017, when this calculation was done, if we reduce our emissions to a medium emission scenario, we can carry on emitting greenhouse gases for 20 years. If we manage to get to a low emission scenario, we can carry on for 30 years. If we stay on a high emission scenario, of course, it's very different. And so that just is a way of illustrating what the scale of the change is. And this other diagram is quite useful as well. So if you just look at the bottom of the slide here, you can see the average annual deployment of systems for generating electricity per year. So so basically you've got 50 gigawatts per year of coal, 20 of gas, 20 of nuclear, 15 of wind, and 4 of solar. So we're still very heavily dependent on increasing coal-fired, gas-fired power stations. If you look at what you would need to do if we take action now, then we would be needing to deploy 80 gigawatts per year of carbon capture of gas, but with carbon capture and storage. So that's where you capture the carbon dioxide and bury it underground. 52 gigawatts per year of bioenergy carbon capture and storage. So that involves growing a lot of biofuels. Where are you going to grow them? That's an issue. And then burning them and capturing the carbon dioxide. 83 of nuclear, and 48 of wind, and 23 of solar. So you can see that's very different, and a very different scale to what we're doing currently. If you wait till 2030, the situation is even more difficult. So these types of calculations give you an idea of the scale of what is needed in order to make these changes. These are not easy changes to make, and it does mean we need to focus on some of these things. Of course, in the last few weeks, very large changes have been made, but of course most people regard those as temporary. So I think it's an interesting time to be having this discussion. So another thing that we can do, as well as looking at how much we need to reduce emissions, we have to bear in mind that the temperatures will carry on going up, even with the carbon dioxide that's already in the atmosphere, because it stays in the atmosphere for around 100 years. That's its half-life. That means that we're already committed to some changes in climate, and with the gradual changes that we might see in emissions, we're going to have more changes. So one of the things we need to do is understand how the climate is going to change and how we might respond to that. So what we are able to do with the climate models is to give an indication of the types of change that we would expect in the future for the UK and internationally. So we produce what we call UK climate projections, and the Met Office produced a new set of these last year. I was involved in the previous set about 10 years ago. And what you see here is just an illustration of the sorts of change that we're looking at. So this is change in sea level. And you can see that the red bars show the range in high emission scenario changes in sea level for different places: London, Cardiff, Edinburgh, and Belfast. And the blue bar shows the low emission scenario. So you can see, even with a low emission scenario, you're looking at changes that could be anything from between, say, 30 centimetres and 70 centimetres. With a high emission scenario, it could be over 1 metre. And these don't take account by 2100 of what might happen if large amounts of the Greenland ice sheet or the Antarctic ice sheet were to melt or to collapse into the sea. That would give rise to an even larger change in sea level. That the problem with those changes is that they're very difficult to quantify, because they're low probability but high risk events, and so they're not represented in the models. So we can give an indication in qualitative terms, but not in quantitative terms. Another illustration which is quite helpful to people, I think, this is quite an old study now, but people find it very compelling, is understanding the risk to infrastructure. So on this diagram, you can see a piece of work that was done for the energy sector. It was commissioned by the National Grid, but involving a lot of energy companies. And what they looked at so the Met Office scientists looked at the climate part, and then they had engineers who were understanding how some of the technology work, the transformers, cables underground, that sort of thing, to come up with this diagram. which basically shows that as things get more red, that means that there's a significant impact and you need to do something. So there's some things like cables, if you look at the one in the middle, that here, you can see that it's green up until the 2040s and then it goes red, whereas other ones are red right from the beginning. And that's just telling you that when you're designing new infrastructure, you need to take account of climate change. When you're thinking about how vulnerable your infrastructure is, you can use this kind of information to help you to understand that. And it's just a simple way of summarizing what's a very complex, detailed report. So one of the other things that the last thing I wanted to mention really was how, in terms of responding to climate change, it's not about looking at climate change in isolation. It's really important that we look at it in the context of the Sustainable Development Goals. Climate is usually not the only driver that is a risk factor. And indeed, if you just look at climate change in isolation, you can come up with the wrong answer. And a very good example of that is what's happened in the UK with air quality and climate change, where in the early 2000s, the government was very keen to promote diesel cars because they produce less CO2. And so they would reduce the climate change impact. And there were assurances that they could clean up the cars and it wouldn't have an impact on air quality. As it turned out, it did have an impact on air quality, and they didn't have enough weight given to that impact. And so when you look at these problems, you really need to look at the whole picture right across, a number of different aspects. For example, if you're going to grow biofuels, does that mean you'll have less land to grow food? Does it mean you'll have less land for ecosystem services, for virgin rainforest or just wildlife, and that can have very serious impacts as well. So we have to look at the problem in the round, and this diagram is just a way of illustrating that. Really, is saying that if you do that, you can often find that there are things that you can do that are beneficial to both things that you're looking at. Whereas if you look at one problem on its own, then you can come out with the wrong answer. Now, climate models can help you with that because they can bring together some of the information on different aspects. You can feed the output from the climate model into other types of models where you can understand other sorts of impacts. And so it's really important that all of the different disciplines work together. And one of the problems, I think, in modern science is that people become very specialized in their field. And actually, these days, we need people to be able to understand a broad range of fields in order to actually help us to respond to these significant societal and environmental challenges. And it's only by bringing together the disciplines that we can actually solve some of these very big problems. So I will finish there and invite questions.
Thank you very much, Vicky. So I've just sent a prompt for some questions, and the first one started to ping in. Just like to first of all say thank you very much for a fascinating lecture, and if people want to express their approval, then they can use, there's a reactions button, which you can, I don't really know what the effect of it is, but I just tried it. I get a clapping symbol, so I don't know who gets to see that. But thank you very much. So the first question is from Jay. And it says, it's asking about the chances of methane release from tundra and what the chances are there of some runaway effects. I guess we're talking about positive feedbacks there.
As the temperature increases, there are significant risks of releasing methane, both from tundra and also from beneath the Arctic Ocean. There is methane trapped underneath the ocean, and those processes have only really started to be included in climate models fairly recently. So there are some model runs now that include some of those processes, and it is a significant risk. I think it's not that well understood how great the risk is, and of course, as you go forward, it becomes more of an issue.
Okay. Next question is, and so I'll just say, if you want to follow up on any of those things, you can always ping another message and I can come back on. So Martin Hawley is asking about whether you could comment on the development of computing that's been needed to develop and advance these models.
Yes, that's a very good question, actually. I should have mentioned that. That's absolutely critical. Generally speaking, the science has been a bit ahead of the computing in terms of what can be achieved. We've always been pushing for having more and more resolution in the models. I mean, I showed you the diagram of where we divide the world up into little boxes, but how small you make those boxes obviously has an impact on how well you can represent the climate. And it's not just a question of getting the detail right in a particular location, because you can do that with regional models, but it's also a question of getting the processes right, capturing the essence of the weather, if you like, to make sure that we can actually understand that better. And having the bigger computers is absolutely vital to that. The Met Office had a very big injection of computer power 5 years ago, and that made a significant difference to the detail they were able to provide, and the value of the projections they were able to provide for the latest climate projections. It's becoming more and more of an issue, actually, because the technology is such that the latest computers, that because of constraints of size of photons and stuff, and also the amount of heat that's produced in a high performance computer, we're now getting to the point where Moore's law is no longer applying, which Moore's law basically was saying that computer power would double every 18 months, and that's not really the case for high performance computing anymore. And the technologies that are becoming available now for things like gaming and that sort of thing don't lend themselves very well to the weather and climate problem. So what people are having to do is to rewrite the weather and climate codes completely and restructure them completely in order to be able to use the latest technologies that are becoming available. So that's an enormous challenge, and it's one that it's interesting that the meteorological community is going back to the mathematical community and asking them to get much more involved in this, to help to solve these sorts of problems. And because, and also, people with computing skills as well, because it needs more than one disciplinary type, even in this kind of fundamental level.
And so, are there is the people pipeline providing in that area, or are people going off to get jobs in industry working on AI or something like that instead?
That's a good question. I mean, I think people are interested in the challenge, so that's certainly the case. I mean, there's an interesting reflection on that. One of the people, Exeter, Beth, I've forgotten her surname, Chris will know it. She's from the US, and she said that the funding in the US doesn't allow for this kind of cross-disciplinary work. In the UK, we're much more switched on to this, and so actually there is the opportunity in the UK to do this kind of cross-disciplinary work, which some funding models don't actually allow. But the other aspect that you mentioned about people going into AI is in terms of looking at the output from computer models, both weather and climate. We're looking at using more machine learning techniques and artificial intelligence techniques for some of the applications of weather and climate, and actually getting people to work in those sorts of areas is quite challenging, because there is an awful lot of competition for the people with those sorts of skills.
Okay, next question is from Sarah Burton, asking about air quality. So, we've seen big improvements in recent weeks on air quality. What's your opinion on this, and how we can continue to keep air quality better in the future?
Well, I hope that things like this lecture, the way that we're all working, having meetings on Zoom, will encourage us to continue using these technologies to help us to do our jobs, to communicate with each other, rather than always having to meet up in person. And that is one thing that will help. I think maybe re-evaluating what's important to us is something that we may do. I mean, some of these things will happen, I think. Some of them might be a bit optimistic, I think. But as people who are clearly interested in climate change, as all of you are, I think it's important that we encourage that debate to happen in the right way. Obviously, a lot of people are concerned about the short-term safety issues at the moment, but I think it does. When we see, particularly people living in cities, and I'm very lucky we live in the countryside, but if you live in a city, I'm sure you must have noticed that it's much more pleasant walking down the street if you're able to go out for your daily walk. But there are huge benefits in this, and that somehow we need to retain some of those benefits, whilst obviously also returning back to a normal life.
Okay, thank you. Adam Blakey's asking what approach we should take to make sure the general public understand the science.
So I think, I mean, this comes back to my point at the beginning. When when I look at a graph, it immediately means something to me, and I think probably half the people in this audience possibly as well, maybe more. Whereas when many people look at a graph, they are frightened by it sometimes, or their eyes glaze over. I mean, I've seen very senior politicians, when you show them a graph, they just don't get it. And these are people who you're wanting to run the economy. That's slightly worrying. So I think education is really important, that people understand what science is, so they understand, they have a reasonable grasp that they're not frightened by mathematics and they can understand a graph. They also understand that science is not about, when you do science at school, particularly, when you're younger, you do an experiment and you come out with an answer, and the teacher says, oh no, that's the wrong answer. Well, there is no wrong answer in science. It's just that you did a different experiment, to the one that they'd intended. And I think people don't understand the scientific method. So you sometimes get with climate change, people either thinking that the climate projection that I show you is the truth, that's what's going to happen, which isn't the case, or that it's just complete fabrication, and that I've massaged the model to give me the answer that I wanted, and that also isn't the case. So it's understanding what the scientific method is and what these models can actually tell you. And one thing about this current crisis is that people are talking about flattening the curves and looking at graphs. Maybe people will understand mathematics, statistics, and science just a tiny bit better than they did before.
Thank you. Just been provided with a nice large drink. Okay, so there are lots more questions, but I think we can save some of them for discussion offline maybe. There's a couple that I think I might kind of join together, which is questions around how the models are tested, whether there's consensus across the globe in different groups that are providing models. And I had also written down the question of where some of the curves have got kind of error bars or confidence intervals on them. So, and I think that's very important also for communicating with the public. How do we communicate how confident we are about the model predictions, what the uncertainties are around them, and so on?
So I think it's really important that we have rival models, and I mean this is something that's been brought up recently with regard to the way the government is responding to, and perhaps using one set of models more than others. And so there's a friendly rivalry amongst climate modelers, as there is amongst all modelers, and they're going to try to make their model better than somebody else's. They're going to put the latest science in it and can compare it with other people's models. But the way that we evaluate the models is to compare it with the real world. So in a climate model, in a weather forecast model, of course, you can do that every day. So you get statistics on the forecast, statistics on the weather, and you can compare whether it's doing a good job. Now, for the Met Office, because they use the same model for weather and climate, that of course helps them with their climate model as well. But the other thing, for a climate model, obviously you compare it with past climate, and you can then look at not just average temperatures, obviously, but regional weather and climate, and compare it in quite a detailed way to see whether it's giving you what you've seen in the past. And it's worth bearing in mind that these models are not empirical models where they've basically fitted to the past data. They use the physics of the world. So they're using the Navier-Stokes equations. They're using the physical understanding of cloud, and they represent that in the model. And then you're testing that against the data. So you have got an independent check. You're not actually training the model with one thing and then testing it against the same thing, which does happen in some fields, because that's all the information that you have. But in weather and climate, that is not the case. They are independent of each other, largely, not completely. So then they have a kind of beauty contest between models. People vie to see who's the best model compared to the past climate. There is a risk there that what will tend to happen is if somebody's boundary layer scheme, for example, seems to give very good results, everybody else will think, oh well, I'll use that boundary layer scheme as well, which could mean that the models all look a bit the same. So that's something that you have to bear in mind. In terms of uncertainty, you can do that by comparing them. So the IPCC do it by taking all 15 or 16 different global models and comparing them and getting a range of uncertainty, which is what those graphs that I showed were. The Met Office have gone one step further and actually taken their own model and generated a whole set of new models by varying the parameters in that model to give a wider range of uncertainty. And then they compare that with the IPCC models as well. So that allows you to quantify the uncertainty. So those error bars I showed you on the sea level rise use that information. But of course, they can only use it on the things that we actually model. So I mentioned about Antarctic ice, which is not represented in that model. That's not represented in those error bars. That's given qualitatively in the report itself. So there's a range of ways that we do that.
Okay, maybe can I have one final question, which again links to a couple of other things people have raised, which is the kind of link with coronavirus now. So we're again relying a lot on models there to predict what's going to happen or how policy should change. Are there lessons that can be learned from climate modeling for coronavirus modeling, and also the other way in terms of maybe how we communicate things, and also model complexity? Should we have very complex models that we can't do like formal parameter inference on, or intermediate complexity of models? I guess there's a lot of common questions that must arise in these very different problems with different timescales.
Well, I think that the key is having enough information to actually constrain your models. So one of the big issues with coronavirus is that it's a new virus, and whilst the knowledge about it is increasing rapidly, there's still an awful lot that's not known about it. With climate, obviously, there are many things that we know about the climate from past climate. And my view of climate modelling is that up to around 2 degrees of warming, actually, we can probably characterise the warming pretty well. I mean, we may not be able to do it perfectly yet, but we could imagine that we would be able to. The more we improve the models, I think it does pretty good job. And because we can compare, a 2 degree world in the UK, for example, with something that's already in the world in another part of the world. So some of the processes will be similar. Once you start to get to 4 or 5 degrees, you're starting to get the sort of feedbacks where methane is released from the tundra, as somebody mentioned earlier. You're getting into a world that looks like something that was millions of years ago, when we have very, very little data. So you're getting more into that territory that we're seeing with coronavirus, which is a new virus because which we don't understand. And actually, it may be that our models aren't telling us as much about what might happen. But that's not to say we should wait for it to get to 4 degrees and then worry about it, because actually life would be pretty difficult at that point. But what it does say is that we can't actually say exactly what it's going to be like in the future. This is giving you a risk analysis, giving you a warning. And I think the same thing you're seeing with the virus is that, people are saying, how are we going to come out of the lockdown? And actually, the models are not the only thing that can give you an answer to the fact they can't give you an answer to that. It's a bit of a trial and error happening there. With coronavirus, what the outcome of that is in 2 or 3 weeks. With climate change, you have to wait 40 years. Mm-hmm. So if anybody's got an idea of how to solve that problem, I'd be very interested.
Okay, thank you ever so much. It's been really fascinating. And as I say,